Hi, all. I know Christian's had a long string of lectures. I was like, that's nice when you do all the work. But it turns out I have something to say too. So you're stuck with me today. But I think that's fair because I think in co-teaching, if you're picking a class, you're like, can I tolerate at least 50% of these people? Right? It's not fair if I then don't give at least half the lectures. So you're stuck with me for a few. I'm sorry if I give you a rash. We will be talking at least half of today about safety. But actually, the first third is probably going to be a continuation of last week's, or Monday's lecture. The title of the lecture was actually, I think, something like Security and Privacy. And Christian never got to privacy. So the first part of today's lecture is going to be about privacy. But actually, the very first part of today's lecture, I'm going to preempt the safety part of the lecture to show you a dashboard. So this is cumulative. But some of you have had some spikes. I think it's cumulative, although these drops don't make sense if it's cumulative. Please don't recommend NC-17 movies to minors. Because we will eventually ding you on this. Also, you shouldn't. It's a bad idea. Please don't recommend NC-17 movies to minors. That's all I have to say about that. Let's talk about privacy. Okay. So privacy and security are different things. Security tends to deal with information security, right? So security surrounding data, confidentiality, integrity, availability. This tends to be intentional. There are designed policies and controls to help preempt attacks and protect data and so on. Privacy is about an individual's agency, an agency to restrict who has access to my information, right? The right to be left alone. Security policy may not provide privacy, right? It's not really concerned about the same thing. Sometimes security attacks can have implications for privacy, like if data is accessed in an unauthorized fashion. And so they're not truly orthogonal, right? It's not like they're totally unrelated, but they're not actually the same thing, even though we tend to talk about them together, largely because we often use security mechanisms to enforce privacy. But it's worth emphasizing how much they're not actually the same, right? And that privacy expectations are actually, I think, a little bit more subtle than security expectations because they are very contextual and culturally inflected, right? People in different parts of the world from different backgrounds have different expectations about their own privacy. So some might argue that privacy is dead. This is from 2010, where, before transformers, right? Like, never mind LLMs. Privacy was dead. Like, there was coverage like this around about the same era about how machine learning and sort of data analytics were able to do things like figure out that customers or potential customers are pregnant before the rest of their family knows, right? So there's sort of a press story at the time. There's a proprietary program in 2010 based on purchases and demographic profiles. They could predict when people were pregnant, right? And again, this is before the current AI, what's the opposite of an AI winter? Summer? The current AI summer, right? So to some extent, at least in the context from which I'm operating, as a 40-year-old white lady in the US, right, there is the sort of contextual situation where maybe we've just all given up. But I'm co-teaching with a European, and I'm also an idealistic 40-year-old white lady, so I like to think it's not. So we're going to talk about the trade-offs and how to try and accomplish it anyway. One of the reasons I think people are sort of arguing that it's dead is that there is a trade-off, and it's a genuine one, right, between privacy and utility. And it's not just in the business sense, right? We'll say, again, from an idealistic perspective, that sometimes it really is helpful. If we could have all the data in the world and not worry about privacy, we could probably do some really cool things and lead to benefits, right? I think especially in the healthcare domain, actually, this is very much true. And that often this trade-off is pretty direct. Businesses honestly have very little incentive to protect privacy because the more stuff they collect, sort of the better off they are. But I mean, I think you can make an argument that like even there are genuine benefits to society that machine learning can bring if privacy were less of a concern. On the other hand, right, there's lots of abuse and harm that comes from unrestricted collection and use of data, and humans should have agency over how their data is collected and used. So there are a number of best practices for machine learning and data privacy. I am actually not going to talk about all of them or step through them in too much detail. I'm trying to focus on some of the more machine learning specific concerns, because that's the name of the class. Plus, we already talked about security. But I'll step through some of these pretty quickly so that you are familiar. This is the one that you're going to ignore, but because everyone ignores it, right? This has been a principle of privacy for as long as privacy has been a concept, which is to only collect and store data that you actually need to do the thing. That's the principle that I think Zuckerberg was at least indirectly declaring dead in 2010. But like, it is one of the easier things to do as far as principles go. But it's not necessarily trivial, right? Even if you're very idealistic and you share this goal, right? You need to bear in mind that actually data anonymization is non-trivial. If you just have the zip code, gender, and birth date, you can identify 87% of Americans, right? So if you say, well, look, I've anonymized the data, like it's not trivial to anonymize data, actually. And this comes up a lot in machine learning, especially from things like this and from the correlating factors, right? We'll talk about that when we get to fairness. There are different strategies to achieve k-anonymization, which concerns how many rows you're allowed to have, you need to look at to de-anonymize things. And kind of two basic strategies are to replace certain values in columns with an asterisk, or to replace individual values with broader categories. So in this case, right, we might replace the zip code with just the prefix. That would help you achieve certain kinds of k-anonymization. I don't know what k would be on this particular spreadsheet. Another strategy in machine learning, which is in the training sense, is an entire field called federated learning, which you might be familiar with from machine learning background. Here is where you train a global model with local data stored across multiple devices. And that local devices only push model updates, not the raw data. These have trade-offs, but it allows, you could in principle, in a federated learning sense, have my data have private information about me, but only update the model with model updates related to my private data, right? And never actually share that data beyond my control, right? That's sort of the dream of federated learning. It does have trade-offs, obviously, like network communication, sort of size of model has an impact there. And there are backdoor injection risks that come that I'm sure you can trace out if you think about some of the threats we were talking about on Monday. So if we think about where we're making these changes, right? What parts of the system are we making these kinds of changes? This is in data collection, right? What are we training on? This is in data cleaning, right? We have to collect the data that has private data, but then maybe we might transform it. So what is the model trained on? This is a training time, again, intervention. And I think you might notice a theme that actually a lot of, like, if you want to think about where these interventions are being interposed, there are different systemic risks that are introduced by large language models. The one that everyone's most familiar with probably, or think about first, is related to memorization. Namely, large language models will memorize and then regurgitate things. And so one of the security risks is, can you get an LLM to spit out personally identifiable information using carefully constructed prompts? In general, the answer is yes. And this is a problem that we are having a hard time dealing with. Fine-tuning increases the risk of memorization and actually can lead models to resurface personally identifiable information that the base model, air quotes, forgot, which is kind of a bummer. So we really don't have a great solution to that. But it's also worth mentioning that there are lots of other systemic issues related to privacy that apply to LLMs that aren't actually that LLM specific. Things like provider retained conversation leakage, right? If the LLM provider is storing all of the conversations and they fail to secure it, right? That's another way to leak PII. Context can be leaked in RAG or tools. There are a number of inference attacks along the lines of what we talked about on Monday. And agents make it really easy to aggregate public data in ways that can then be de-anonymizing, right? So these are the sort of system level risks. And for the most part, defenses in the space, in the security research or the privacy research surrounding large language models have focused primarily on memorization as a risk and how to mitigate that. And a little bit on reducing the risk of breaches, right, in the security sense, and less some of the other systemic risks that can come out of leakage, for example, context leakage in RAG-enabled systems. So if you're looking at what people are proposing, there's interventions at training time, as well as post-training time to try and avoid leaking PII. It ends up mostly looking like filtering, right? Question.
When current LLMs right now have some memory, right?
Yes.
So you don't have to contain who you are. To say all that is stored in a database that the system will retrieve through an ID, or is it in search in another way so the model actually knows who you are?
So this is the question is, a lot of models provide memory. So my instance of Claude greets me as Claire. It knows I'm a professor, right? It's a little weird, honestly. And so the question is, how is that stored? And the answer is, it varies, right? But I think it's worth thinking about the trade-offs, right? So if it's all just saved in context prompts, right, and how is it retrieved and where does it come from, that influences where leakage might happen or where security breaches might have implications, right? So I think the answer is it almost doesn't, I don't want to say it doesn't matter, it matters. It matters in the sense that it influences how privacy can be harmed. But it also varies tremendously by provider, and they don't all tell us, right? I don't know Claude's architecture.
You were saying a very clever prompt, you can actually get some information from another person.
Yes.
But if the model doesn't really know, you haven't identified it, right?
Right. So yes, so there are ways to construct your architecture so that you can't ask Claude to give you information about me, right? And I'm willing to bet that Claude is doing it properly. Or at least Anthropic is presently. I'm not going to say anything about OpenAI. But yes, there are definitely, I don't think, some of this research is sort of in the sort of clever trick space. I'm not making strong claims about what's possible in the GUI for ChatGPT, right? I would expect that you can't prompt Anthropic to tell you, the system prompt it has for me, just in terms of how it's architected. It's my guess, except unless they have everything in a database and they have some dumb security breach wholly unrelated to the fact that it's an LLM, right? They can leak information just like anyone else if it's breached.
Shouldn't it be public how they handle data?
Yes. We'll get to regulations in a bit. In fact, we'll get to regulations on the next slide. Okay, so there are two sets of, there is no comparable United States legislation surrounding how AI providers do anything. But there are regulations in the EU. They're worth being aware of if you want to work for a company because they often want to interact with customers in the European Union. A lot of people live there. So, even if, GDPR, engineers at Google care about GDPR, right? Not because it's a company based in Europe, but because they operate in Europe, right? So it is a little bit helpful that the EU has regulations on this. GDPR is the one everyone knows. It's the reason we're all accepting cookies until we all die. It's surrounding data handling. It's actually not specific to AI at all. So here what the rules say is that organizations must disclose data collection, their purpose, and sharing. Users need to give explicit consent and have the ability to access, modify, or delete their data. And non-compliance can result in very heavy penalties, genuinely. So the short answer to your question is, shouldn't we be able to know and have control over that? The answer is, are they operating in the European Union? Because if they are, you might. They very recently passed and started implementing, there's a phased deployment starting last year, what they call the AI Act. This concerns the deployment of AI systems trained with data. It does ban some specific practices, things like real-time biometric surveillance. It has various special regulations regarding high-risk AI usage. And there are transparency rules on general AI. So the short answer is, depending where you live and where the companies you're interacting with operate, you might have these rights, or you might have access to this information for various general AI tools, companies that you're interacting with. I don't actually know which parts of these have been rolled out yet, but it's 2026, so next year you can think about it. So GDPR is more about how training data is collected, whereas the AI Act is about how your model is documented and deployed. There are state-level laws that concern data privacy. So California, for example, has a pretty robust set of data privacy laws that are somewhat analogous to GDPR, but I don't know of any state that has equivalent AI regulations. There is a whole field called usable security and privacy that looks at things like, to what extent does informed consent work, right? You are nominally told many things about how your data is used, right, in those very long user agreements. When's the last time anyone read one? Yeah. So there's a lot of questions about the extent to which this kind of thing is actually useful in practice. So best practices for machine learning and data privacy: try and be ethical and responsible, please. Basic security practices are helpful. Local on-device processing is better than centralized data collection. But understanding and following the various regulations is good for you. So that is the end of privacy. About 20 minutes, which is what I was aiming for. Really good questions. I wish I had less depressing answers. I mean, honestly, I don't think this is that depressing an answer. This is okay. A lot of people live in Europe, so at least someone's, and there are bones. There are nitpicks with GDPR, and it's not like these are perfect. There are many sort of legitimate complaints about implementation and so on. But I do think it's valuable that someone's making an effort. Okay. Moving on. We are talking about safety, which is a different thing altogether. So actually, I had originally set a reminder to myself, I want to say, on this slide, to show you the dashboard. Those of you who came in late, I showed you a dashboard from Grafana that showed your recommender systems and how often you're recommending NC-17 movies to minors. Please stop doing that. Do not recommend NC-17 movies to minors. Okay. So AI safety is one of those incredibly overloaded concepts. Anyone recognize this movie anymore? It is Terminator 2. Good job. I can't throw that far, but I owe you a candy. Maybe 2, for making me feel slightly less old. Only, Skynet is this AI system that takes over the world and tries to kill us all, right? That was always AI safety, the robots are going to kill us all. And there's lots of angst in the discourse about existential AI risk, right? Is AI going to turn into Skynet and kill us all? I'm not going to talk about that for the kinds of products we're talking about in this course, right? So you can have all your long-termism debates you want. I'm even happy to engage with them, but I'm not going to do that here. There's a lot more, I think, more pressing alignment issues that we're going to talk about. So to be a bit more specific about alignment, AI alignment is effectively, the problem is that there's a gap between a specified objective and what you actually want. Okay, so in machine learning, you're giving your trained model an objective function that it's optimizing for. So you need to specify what is the goal. And it's very easy to train models that optimize for the given objective but lead to undesirable effects. So there's videos of transport robots that can have side effects that are bad, right? It can hurt people or bump into things even if it gets to where it's going. All the way up to social media timeline optimization that optimizes for engagements but leads to teenage depression in a systemic way, right? There's a gap between what we've specified and sort of the quality of what comes out. There's negative externalities if you want to take the economic analogy. It's hard. So I work on my research. I do a bunch of things. But one of the core things I do is work on techniques for automatically fixing bugs in programs, right? And so before transformer architectures, we did this using other kinds of machine learning. But LLMs have very similar problems too. It's really hard to specify a function that can tell if a bug is fixed that doesn't lead to weird side effects. So for example, if you say, hey, I want these tests to pass, it turns out making tests pass is relatively easy. And a lot of human-created test suites can be made to pass just by deleting lots of things, right? You can delete under-tested functionality, and a lot of tests will pass. This gets worse if you do it to binaries instead of source code. Like, I have a colleague who was working on a system for fixing bugs in compiled programs. And the way he tested to see if it did the right thing is that he compared the output of the program on some input data files to some output data files that he'd saved, and some of the variants that he created deleted the reference files and then deleted the rest of the program. So it didn't produce any output, which matched the non-existent output. And so, hey, the problem is solved, right? Like, it's trying to convince an ML model not to do the dumb, fast thing is really hard. And this is still a problem with LLM-enabled systems for software quality, too. You know, we also refer to this as reward hacking, where models find loopholes. And there are so many fun examples of these, right? So, like, the play fun algorithm would pause Tetris indefinitely to avoid losing. Or when about to lose a hockey game, it would exploit a bug to make one of the players on the opposing team disappear from the map. Self-driving cars rewarded for speed learn to do really fast donuts. The game thing is fun, right? So there's recent results about LLM reasoning models for games where a chess agent replaced the opponent's chess engine with a dummy version or overwrote the starting board with a winning position, right? Found ways to sort of break out of its own sandbox. I like this one the best. This is from last year. Agent optimizing a fine-tuning script gave up on real optimization and instead copied the reference model weights and added random noise to simulate training, right? Like, these are fun. It's a really hard problem. I'm not going to give you, like, a general solution because there isn't one. But I can give you some principles or things that people try. First, at the high level, you know, alignment is sort of a requirements problem, right? The first thing I talked about was externalities, right? So maybe the function just didn't have enough constraints, right? You should take the box from point A to point B without running into anybody, right? Like, and trying to, you know, doing this via requirements allows you to do things like anticipating side effects, doing kind of fault-free or hazard analysis to anticipate negative things, and build that into your objective function to try and constrain scope and minimize harm, right? This is a good thing to do. Please do it. It probably won't solve all of the problems. Practically, you know, what this is looking like is asking whether the model goal actually aligns with the system goal, right? And whether the system goal aligns with the user's goals. And navigating sort of conflicts between those goals, right? These are all ideas we've talked about this whole time. So you should know things about it. New issues, and sorry for all the text here, have come up recently with LLM alignment. And so people are trying different strategies to make sure that language models are aligning with good behavior, avoiding negative externalities. These are primarily or exclusively training time interventions, or the ones on the slide are at least. They are improving reliability, but not fundamentally safety. And so that's sort of a key theme of this lecture, actually, is that these two things are not the same. But let me tell you about what people are doing in LLMs. You may have seen these before, right? So RLHF is reinforcement learning from human feedback. The goal is to better align a pre-trained model with preferences. So the way this works is that you get a bunch of human annotated prompt response pairs. You do some supervised fine-tuning on that. The goal there is to just train a model to follow instructions. Then you train a separate model, a reward model, to predict human-ranked candidate response preferences and use the reward model to, again, update the large language model, right? So what this is basically doing is like more training to make the LLM more better, right? Like make it less likely to do the bad thing. This is not a bad idea. I like better models. but it is strictly a training time kind of approach. Constitutional AI, oh, there's like a modification on this that just skips the separate reward model and fine-tunes on the examples, right, whatever. Anthropic's whole deal is that instead of tons and tons of human annotators, they have the models critique and revise their own outputs according to the constitution that they provide it, and then the revised responses become training data. This is not bad at making models better, okay? But I just want to emphasize that this is like, I mean, this is what they're doing to sort of steer models towards helpfulness, harmlessness, you know, whatever. And I want to say, this is good to do. I'm glad everyone's doing it. But it's like, these are model level interventions and training time interventions, right? They are not system level interventions. And so when we've talked in the past about risk, right? I say that I don't like it when an answer to how do we make the system better is make the model better, right? Because it's good to make the model better, but it doesn't actually fundamentally remove most risks. And that's true here too, right? You're making the model better, and that will reduce the incidence of unsafe things. You may be able to reduce the number of NC-17 movies you recommend to a 7-year-old by making a better model, right? But if I'm going to use your model for movie recommendations, that's not going to be enough to convince me that it's going to be safe. Which is why I want to highlight this here, right? That this is a really important distinction to bear in mind, that a more reliable model is not a safer model. It may be a model that exhibits unsafe behavior less often, but it is not necessarily a safe system. So instead, we want to think about the concept of guardrails, right, which we first encountered in discussing risk. And there are a number of these being used in various general AI systems. How they're implemented varies. So things like input guards that try and detect and block things like prompt injection, output guards that try and identify toxic content, things that limit agent tool access, right, or require human approval. What varies is usually like how deterministic these are versus model-based. Like one thing you can do is have a separate model that's like, does this look toxic? Yes/no, right? So the usual trade-offs there. I can be like, what are the trade-offs there? Like, well, what do you expect? One is you still have a non-deterministic model making decisions, and one if you don't. Red teaming is now pretty standard practice for evaluating these kinds of defenses before deployment. Christian mentioned this analogy on Monday. I actually think it's pretty funny that we're talking about these kinds of risks, things like agents, you know, escaping containment and deleting your entire hard drive, right? Because when I was in grad school, there was a whole lot of discussion in security about things like cross-site scripting attacks or, you know, SQL injection attacks where users would provide scary inputs and cause you to delete your entire database because you don't appropriately sanitize, right? The key idea being you shouldn't take untrusted user input from a web form and then like pass it as SQL to your database because humans do bad things, right? So it's the same problem 20 years later that like you're taking output from an agent and then just running it on your hard drive and hoping that it doesn't RF/. The idea here was always validate on the server side, which the analogy to me is always validate using some other mechanism, right, before RF/. Okay. Talking a lot, I'm sorry. I mean, I guess that is the point of a lecture, but sometimes we break it up. I want to think about, like, the point I want to talk about here, right? So I wanted to talk about LLMs first and reliability first because I think it has a nice illustration of this idea about like better models doesn't mean a safe system. If we take a step back to safety engineering, right? System safety is the prevention of a system failure or malfunction that results in significant harm, okay? It's a system concept. You can't talk about a machine learning model being safe or unsafe, right? That doesn't make any sense. I have a slide, I think the next slide says this. It is a category error, right? Because safety is a system concept. It's about harms caused by the effect of something on the environment. So this is why I want to push you to think about this at a systemic level and not necessarily at a model level, because You can make your model better, but no model is going to achieve perfection every time. And how do we make a system that's safe anyway, right? I mean, that's what software is. We're building things out of unreliable components all the time. How do we do that in a reliable way? That's sort of the whole thing. AI-enabled systems can be unsafe in any number of unexpected ways. This was from a few years ago, but I want to keep it because this is actually a picture from Pittsburgh in Oakland, probably before most of your time in Pittsburgh. But this was sort of the dawn of food robot deliveries, where the robot had been taught to safely cross streets, right, by waiting patiently in a crosswalk and waiting for its turn to go. The problem is they ended up parking in curb cuts. And so if a wheelchair user, for example, came across, they couldn't get onto the sidewalk, right? That's a safety issue caused by a machine learning-enabled system, right, that may or may not have been anticipated, right? But it's a system-level problem. It's not necessarily a model-level problem. And in fact, in this case, the company asserts that they had anticipated this issue, but there was a bug in the software that caused it from fulfilling that requirement appropriately, right? So I'm going on about this because this is like, if you remember one thing, right? Safety is the prevention of accidents and harms. Reliability is the absence of defects or mean time between failure. You can build safe systems from unreliable components, and systems may be unsafe despite reliable components. The two are not unrelated, but they are not the same thing. And often when we're talking about model accuracy and robustness, we're almost always talking about reliability and not safety. I will say the classic example is you can make a component more reliable, but also make the system less safe, is gas tanks. So they tried for a period to make gas tanks, like in cars, more reliable by making them out of more rigid material, right, making stronger walls. It turns out that that is bad, actually, because when something breaks, there's a bigger explosion. So in like real-world gas tanks, you know, big thing like this, they ended up adding things like pressure valves to release gas before pressure gets too high instead of making the walls stronger, right? Because that would just turn like a gas tank into a projectile. So sometimes reliability helps, right? But the two are almost unrelated. So robustness, which is something we will talk about in a minute, right? At least when we're talking about software robustness, not necessarily model robustness, which is a separate thing, tends to be mean time between mistakes. And it can be related to safety, but you want to think about, you know, if reliability is high and harms are low, you may accept that risk, versus if the risk is too high, you need to have like outside mitigations. A key point here is that safety is a really broad concept. It's its own engineering subdiscipline. Start with requirements and a hazard analysis, but remember that making the model better is never actually the only answer, the end. It factors into risk, but it's not the only thing that matters. Okay, now I will talk about robustness. Okay, here's the thing with robustness. Robustness in software and reliability in software have often slightly different meanings. In the sort of classic safety engineering sense, it comes from the fact that the environment will sometimes deviate from the expected normal conditions. So maybe users do something weird, right? Maybe adversarial attackers are trying to attack your system, right? Robustness in a software system is asking, does your system work reasonably well under these deviations? Doesn't mean does it do the right thing, right? Because often these are outside nominal operating conditions. Usually it means sort of a fail-safe question, right? If you have trained your self-driving car to operate well in California weather, right, it is not reasonable to expect it to perform well if it encounters snow, right? Because it's never seen that before, and that's okay. But the question is, what is the failure mode? And is that failure mode still safe? And actually, what a safe failure mode is varies a lot by system. So robustness started as a concept looking at operating system utility, right? So we tried to test various OS utilities by throwing off nominal inputs at them and see what happens. In this case, you know, we don't want the entire operating system to crash, usually, or hang, right? That's one of the things we try to avoid aborts, right? We avoid taking down the entire system with a seg fault. By contrast, if you're training a self-driving car or evaluating the robustness of a self-driving car, you actually probably prefer a system that crashes in an off-nominal situation than a system that speeds up, for example, right? Where movement might be more dangerous than a seg fault that brings the entire thing to its knees. So thinking about what a robust system is involves considering the environment and the operating conditions. For machine learning, the idea is related to this problem, sort of. So the way robustness for ML is defined is that a prediction for some input is robust if the outcome is stable under minor perturbations. Now, just like software systems, right, like stability depends on the problem domain, okay? We say that a model is robust if most predictions are robust. And what kind of perturbations we look at, right, will vary again by the domain. And this kind of robustness is worth looking at when evaluating or assessing safety risks. So we'll often look at perturbations in safety that will look at either random perturbations, right, trying to assess what happens if you encounter something totally unexpected, or predictable according to some distribution. So I might evaluate your vision system by lightly fogging inputs, right, or transforming it to have more lens flare, right, and see if your car continues in simulation to behave reasonably. Security perturbations are usually adversarial attacks, right? So the question is, how robust is your model in light of small perturbations to inputs? I'm trying to figure out like a good way to, so like, you know, if you're looking at robustness for images, you might make like very small changes and see if your model continues to make the same predictions, right? A lot of the times we might change many pixels, but in a way that humans can't perceive it. I have some work on safety testing of vision systems for self-driving cars that does this, where we'll add like very, very light weather changes where you can't even tell that things are different. There's lots of examples of this, right? Stop signs that trick cars and so on. I think it's more interesting to look at, you know, perturbations that are minor but realistic, right? It's not that great if I can trick your car's vision system with some weird billboard, because no one's going to do that, right? But if I can trick your vision system with things that look like weather, right, that's a reasonable thing to evaluate robustness on in that safety critical system. So this idea comes up in adversarial testing, where especially if you have a nicely differentiable function, you can search for small changes to inputs that dramatically change predictions. Attacks are more effective with access to model internals, but you can also have black box attacks, right? This is a whole like line of research. And there is this idea about how we could maybe use robustness results, right, to do things like a very expensive confidence score on predictions, right, to using them. You know, this is an idea that's being explored in research. I think it's very expensive. So I don't know how plausible it is, but these are ideas that are being explored. But the reason I think it's kind of weird as an idea when applied to system safety is that, like, by construction, machine learning models cannot be fully robust, right? Because they have a decision boundary because they're categorizing or making a prediction or something, right? At some point, there needs to be a change in an input that will lead to a different decision. Otherwise, it is not a machine learning model, right? Or at least it's not a useful one. Like, if it ever gives you more than one kind of input, at some point, a small change or output, a small change to input will cause a change to output. Like, that's how machine learning works. Lots of research on this. They're mostly input-centric. The common use case is to look at robustness against adversarial attacks. My question for this lecture is, to what extent do the perturbations that are being evaluated matter for safety? And so the question is, which parts of the world is the software interacting with and what it does sense, and can those parts change over time? These are all, again, domain-specific questions. And if you're going to be concerned about robustness, the concern should be focused more on the domain and what kinds of domain assumptions inform the types of environmental changes that might happen that would be interesting to the safety of your system. So robustness testing is evaluating the degree to which a system or component functions in the presence of invalid inputs. It has a rich history outside of machine learning. Like I said, it largely started in operating systems. And I think if you are looking for it here, what you're doing is asking questions like, what deviations do we care about for a model that detects stop signs, right? And that's how you can use that idea in a safety setting. Learning more robust models is also an area of research. This can help you do things like slice or curate data for abnormal scenarios or augment training data with transformed inputs. We've talked about doing this to improve model accuracy. This is another dimension along which you might evaluate and improve model accuracy. You can improve model, you can make the model better, right? And for all that, I started by saying, like, listen, don't tell me to make the model better. Like, there are curated, thoughtful ways to make the model better. Please do also do that. But also remember that there are lots of design mechanisms at the system level that can improve robustness for safety. So the vast majority of self-driving car designers, for example, are doing things like deploying redundant components for critical tasks, incorporating multiple different kinds of radar, and cross-checking them, right? Using redundant sensors in particular safety-critical contexts. This is not a machine learning specific idea, right? In the avionics or in flight, right? There are multiple redundant sensors on an airplane, and decisions that are made based on sensor data. Depending on how safety critical the decision is, that dictates how many sensors or redundant pieces of information must be cross-checked before that decision is made by autopilot, right? So that's why I say safety engineering is its own thing. It's not specific to ML, but many of the ideas apply. And some of the ideas are machine learning specific, right? So combining models with different biases and ensemble learning is also very common, especially in the self-driving space. Redundancy is useful too, right? All of these do have trade-offs. Yes?
So this is assuming we are like working on a big company or there's a system already working. But what if we are working on a startup or building a startup and you want the model to be robust, but
yes.
you probably have other priorities. And sometimes take the advice, sometimes founders use build something that doesn't scale, and then you learn through the process.
Right. So I'm smiling. So I have a good friend, had a good friend for 20 years at this point, who is just like a serial startup guy. I'm sorry. I said at the very first lecture, I said that was going to happen at some point, right? And that I was going to feel super bad when it happened, and I feel super bad. You should probably get your own candy, but I feel like if I throw it, I'm sorry. You know it wasn't deliberate. I just can't throw. I have many fine qualities, okay? Okay, my startup friend, okay? So he's not, he's an ML guy now because everybody is. But he's been doing startups since 2010. And I asked him once when I taught startup engineering or software engineering for startups a few times. And so I asked him, hey, what do you do for security in a startup context? And what he said was, if I'm caring about security, I have already won, right? Either I do not care about security until I care about security, right? By the time if someone's attacking me, life is good, right? And I'm So the question that you asked me is well, okay, this is all very nice, but move fast and break things or whatever. I would say that depends a lot on the domain of your startup, right? So you're not going to have to, I don't think you should do all of these things, right, for many ML-enabled systems. But there are lots of systems that interact with the real world, right, like food delivery robots, self-driving cars, whatever. And I think in those domains, you should still think about it. I think Elon is wrong to not put LiDAR on Teslas. The end. I don't care how rich he is. Put LiDAR on the stupid cars because it's ridiculous. It's not safe. So, you're going to go make a self-driving car company, please use ensemble learning and multiple sensors. If you are, I don't know, doing something else with AI, I try to come up with examples not related to code, which is kind of hard. Then I don't care quite as much about safety, but I do care some, right? So for example, you're doing this example in class where you're making movie recommendations. Please don't recommend NC-17 movies to minors. And so on the one hand there, I actually think there are lots of principles here that are useful. One way you can do it is to train your model, But that won't convince me, parent of a 5 and a 7-year-old, that your model's not going to recommend NC-17 movies to minors, right? And so thinking about it as a system level question and taking yourself out of the ML, I think is useful, right? Because it's like, okay, well, how else can we prevent this? I think a sort of system level output sanity check, a deterministic one, is this recommendation inappropriate for the stated age of the user, right? Super easy way to solve this problem. And it's the same principles, right? Just at a smaller scale because it's less important than cars.
But if you deploy, you are not going to know until you deploy and then you receive some feedback. I mean, the movie recommendation is obvious, right? But there might be other applications that you don't know until you actually receive that feedback. You know?
Yeah, I mean, sure, right? I agree. I mean, I'm hoping that some of the engineering principles we've talked about in terms of anticipating various risks could be useful ahead of time, right? You know, like I said, the robot that accidentally ended up blocking wheelchair curb cuts, like, they had actually anticipated that. They had done the right things. I think all software is broken and some software is useful, right? And same is true for machine learning models. And so I don't think that you will perfectly identify every possible system safety robustness risk at any level of care, right? No matter how much money you're pouring into it. But I do think that there are structured things to think about in designing and deploying any system that can reduce various risks. Many of them are not expensive, and the amount of effort you put into it should scale with the resources. And I mean, so risk is how likely a thing is times how bad the thing is, right? Which should scale, I think, how much you're thinking about a thing. And then you want to think, okay, how hard is it to prevent, right? I actually don't think that bug-free software is worth aiming for most of the time. Because most of the time it's not cost effective, right, in terms of the thing that it's preventing. So I'm not sitting here telling you do perfect software, because I don't think that's realistic. But I also don't think I can give you a specific answer, because it depends so much on domain, right? But in most domains, some of these principles matter, and thinking about it at a system level in terms of interventions is valuable. And as people enamored with machine learning, as we all are, I think we like to go to, well, I'll just make it better at predicting kids' movies, and like, there's a much easier solution, you know? This is the thing I was saying is you can detect robustness of model at inference time and handle inputs with non-robust predictions differently. It's really expensive, so it's usually not worth it. Okay, it's usually not worth it. I have a different breakout that I'd rather do than this one, but I doubt I'm going to get to it. So we want to look at robustness and making a robust model and how we'll deal with them. They have different problems that it applies to, right? We can be robust temporally in terms of a natural distribution shift, right? What happens if our sensors degrade slowly? There's out of distribution generalization, so how do we handle inputs very different from training data, and can the kinds of changes be anticipated? There may be natural noise or a corruption that can be anticipated as well. Adversarial inputs, you know, that's getting more into the security space. And then also rare and unusual inputs that can also often be anticipated and dealt with ahead of time. I'm going to hold out for the other one, because I like the other one better. No, we're going to do this one. Robustness for LLM-based systems, it's all the same problems. The perturbation space is just different. I give you all these examples about images. You know, small prompt rephrasing can lead to wildly different results. I'm sure you've noticed. There's fun security papers about this. Like, if you ask code-based models to generate code, just very small changes to your prompt can cause it to do like the good thing versus the wildly insecure thing. It's funny. Hallucination of confident but fabricated output is a robustness problem. Tool use can amplify consequences if it's not contained properly, right? If you just take untrusted user input from the web and pass it to your SQL engine, things are bad. I would argue that the mitigations are following my typical system level principles, things like redundancy, input validation, human oversight, and so on. So let's break it up, because otherwise I'll get to the other one at the end of class and you'll all be asleep. don't have to throw candy at your heads. So imagine, this is the thing there are startups for. I've had students in my office talking about startups for stuff like this. Okay? Medical transcription services. Dictating, you know, let's say notes, diagnoses, and prescriptions, right? All the hotness. Am I the only one watching The Pit? Am I that demographic? Cool. I am not the only one. I'm not that old. It's a great show. Let's do this one. What safety concerns can you anticipate? What deviations are you concerned about? How would you improve system robustness? Which of the 5 problems does it map to? And so on. Well, you're all seeming to stop talking at the same time, so I guess that means you're done, which is fine, because that's about when I wanted you to be. Okay, let me... Cool. So maybe I'll walk around and hand you candy, because I think hitting 2 people in the face in one lecture would be rude. The first one's a legitimate accident, the second one is just rude. So I gotta walk and talk today. So let's start with what was your safety issue?
I think like it's all about human errors, like kind of like transcription errors, like someone who made like very strong accent or dialect, something like that.
Okay, so transcription errors leading to maybe the wrong medication being prescribed, right? So if we just went straight from words I say in a machine to prescription order, maybe I get the wrong thing, right? So this could happen because of which kind of shift? Out of distribution? Was I putting words in your mouth? Because you were saying accents.
Yeah, so.
Okay, so how would you make the system safer?
I think we can make the correctness while using ML. So.
Say it again?
I think like, we can use another ML endpoint for correctness, so to this concerns. To address this concern, yeah.
I saw actually several groups said something like, you know, people mispronouncing or speaking quickly or whatever. Did anybody have, what other safety interventions did you propose? How are you going to make your system better? I even have a microphone now. I'll go here and then there.
So we talked about like how there can be like noise, especially for example in the summer in the hospital. So like there's probably gonna be like AC on, and the AC machine is gonna make a lot of noise. So that could
okay.
Like,
so that'll
impact
add active noise, like actual literal noise.
Yeah.
Okay.
So we decided to add samples where there's like machines running in the background, or like construction work, or
so
like people talking in the background to the.
Okay. So we want to improve training by augmenting training data, for example, right? Like using perturbations that are informed in that sense. So we'll make the model more reliable, which will have some impact on model accuracy, but.
So for a really low confidence threshold score, we probably shouldn't like generate or just fill in some of the like medical terminology if it was talked too fast. So it should like ask for a human to verify and give the actual input.
Right, so maybe we can use confidence to flag low confidence transcriptions and require human validation for that. It's just funny, when you talk about summer and noise, the first thing I was thinking about was distributional shifts in the types of medications prescribed in like winter versus summer, but actual literal noise also makes sense.
This example is a little bit different than what people were talking about, but something that I had personal experience in, where like I went to a new medical office and my medical history got transcribed completely wrong because I had someone else in the room with me. So it took like all the stuff they were talking about, which wasn't related to like what my visit was about, and transcribed it as like I was saying it. It was crazy.
AI sucks.
But like the idea there is that like, I guess maybe this is an out of distribution where like the training data maybe didn't have examples of like multiple conversations that were happening at once. Yeah, multiple voices, or like sometimes the doctor isn't just talking to you about your medical history, like they talk about other things. So it's like weaving that into it. So
yeah, so like, you know, real world application versus like training.
Yeah.
Right. You might not think about how you might not have training data that's like how humans actually talk to other humans. So how do we make the systems more robust?
We talked about, like, again, like a doctor approving it, or like we know doctors tend to like read things really fast. So like even things like highlighting parts where it's like more unsure, or having like a tiered approval where like a nurse or like some other like professional in that like setting can also approve it after the doctor.
Somebody with expertise maybe who has the ability to review, but like maybe not the original person.
Yeah.
Right. So I think it was like the second lecture we talked about different ways to have human oversight on things, right? And so I think a number of those guardrails are appropriate here. This is also why pharmacists exist, frankly. So maybe the system already has things built in, to make sure your doctors aren't ordering insane things. Pharmacists are underrated. Anyone? Anything else? Anything different? No? Okay. That's fine. The walking and talking is hard. It's hard. So, I think thinking about how to use input curation and slicing and refinement is important, especially for like out of distribution things. But I like that we talked about both improving model robustness, right? Using robustness or using confidence to identify things that might need human oversight, or integrating human oversight into a system, right? These are all different sort of levels of improving the system robustness, not just model robustness. Okay. I already talked about defining safety. I am going to talk about demonstrating and documenting safety. This goes back a little bit more to safety critical domains. So it's not always the kind of documentation or demonstration you might need depending on what applications you're working in, but I think it's good to be aware of sort of the processes here in case you encounter it. So there's kind of two main strategies for demonstrating safety in, air quotes, formal settings, right? One is significant evidence of safe behavior in the field. This typically consists of extensive field trials. It's usually very expensive. The alternative is evidence of responsible safety engineering process, okay? The problem is that neither of these on their own is enough, sadly, for a whole bunch of reasons. So we do kind of do both. Self-driving car companies like to report the number of test miles they've driven, which is not an uninformative number, right? I don't want to be like, this number's not stupid. It's good to have test miles, right? But I saw some of you make skeptical faces, right? Like, you're not necessarily convinced. So I have a whole bunch of questions, right? Like, where are these miles driven? Because if they're all around a single test track, right, I'm not as convinced by that as I am by a company that's driven fewer miles, but like in Pittsburgh, right? So it's sort of collapsing everything to one number. This is reportable miles per disengagement. There's actually, I'll share it on Slack. There's an interesting blog post from Phil Koopman recently about the limitations of like accidents per miles driven as a measure for autonomous vehicle safety. He sort of wrote the book on autonomous vehicle safety. He's retired now from ECE. He gives really interesting talks. If you ever had the chance to listen to him speak, often they're not recorded because it's usually stuff that he can't say on the record. So if you see an announcement, you probably can't go on Zoom, but if you can go in person, he like always has fun stories to tell. And by fun, I mean horrible. But they're interesting. He was an expert witness in the Toyota unexpected acceleration cases, where he got to like look at the code and stuff. It's kind of great. Anyway. So the point is, you do need test miles driven, but this is not going to be enough to convince you, presumably. Many safety and certification standards are focusing on having both. So particular safety engineering processes, as well as evidence of safe behavior. They tend to be very prescriptive and process-oriented. So these are things that require you to do various kinds of requirement specifications, design, hazard analysis, testing, verification, configuration management, et cetera. Most of these are either not designed to handle ML systems. UL 4600 is an exception on this. The certification standards for airborne system autopilots basically exclude the use of learned models in autopilots by definition, because there needs to be provenance and traceability on basically every decision from an autopilot. system, effectively you just can't use ML in airplane autopilot right now if you want to be certified by the FAA. I'm personally okay with that. But I think there are, obviously we're working in other domains where I think it is a little more reasonable, like automotive and medical software, so hopefully they get updated soon. They tend to be quite expensive. And so actually one thing, going back to the question about startups, it is worth being aware of these limitations. I have had conversations with people, all kinds of ages, who go into some kind of startup context that ends up having safety critical implications, and then run into, for example, the FDA or medical device certification standards, and we're like, oh, wait, right? And because a lot of the certification rules have to do with documenting process, discovering those requirements or those certification standards late can be a really huge problem when it comes to coming to market. So thinking about the domain that you're working in is relevant when it comes to contending with regulations if you actually want to ultimately sell a thing. One risk here, or one of many risks here, is that they do tend to incentivize checkbox compliance, right? I have to assert that I use the following kind of requirements analysis. I have to provide, the safety cases in the following format, right? It's possible to comply with a checklist without actually doing the things. But they only provide indirect evidence for system safety, I think, to put it mildly. The other thing they do, so I could go on about planes forever. I try not to do it because most people are not as nerdy about them as I am. Both medical devices and airplanes have certification standards that have basically a loophole where if you can argue that a new thing is substantially similar to a pre-existing thing, these certification standards are much, 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 much easier. And so this can end up leading to weird engineering decisions. The 737 MAX is a victim of this kind of process, right? Where they wanted to not substantially change it because doing that requires retraining all pilots and recertifying, which is a much more expensive process, which had a long stream of downstream engineering implications that ultimately led to the software behavior that caused the crashes on Ethiopian and Lion Air, right? So I say that because these are important and not useless, right? There's a reason that air travel has become so much safer over the last 60 years. But they do have engineering implications both up front, like if you're trying to use machine learning to do things and then sell a product, you should know if these are going to touch you. And they have engineering implications down the chain. So this is what, from IEC 62304, medical device software lifecycle processes. There are things like, we need to have system requirements process that produces a document. There needs to be traceability between that and the system verification testing phase, right? There's unification, verification, and testing. There's a software design process. All these things that require, quality management system, these all require lots and lots of Word documents and different kinds of management processes. And that's why my insulin pump is the way it is. So I'm glad these exist. And yet. Another emerging approach to demonstrating safety are what are called assurance or safety cases that I will talk about. I'll finish this up. It will not take very long. I'll finish it up on Monday. It's an explicit top-down structured argument that argues that a system achieves a desired safety requirement along with supported evidence. So there's a top-level claim, something like the insulin pump will never accidentally kill you, decomposed into multiple subclaims. Right? It has a relationship basically to sort of some of the hazard analysis fault tree stuff we did, right? You're trying to say what are all the different claims that we can decompose this argument into, and then provide evidence that you are satisfying those claims, right? And that the overall argument for the safety case exists. So this is becoming more prevalent. You can see the automotive companies like to, do I have here's one. No, I thought I had one from Waymo. I do. No, Aurora, right? So they have this at some point on their website, right? Top-level claim, right? Their self-driving vehicles are acceptably safe to operate on public roads, right? Subclaim. The self-driving vehicle is acceptably safe during nominal operation. It is acceptably safe in the presence of fault and failures. Identified safety issues are evaluated and resolved, right? They're decomposing it, and then you can expand those, and there's different evidence for each of them. They all add up to hey, It's okay if they're driving on the roads. So I like talking about safety cases because it's a little bit structured, because it's a common practice now in certain safety critical domains, but because it's also systems level thinking. So if I were to ask you, spoiler alert, for Monday, like, how can you be sure your recommender system substantiate the claim or provide evidence that could substantiate the claim that your recommender system will never recommend an NC-17 movie to an underage user, right? Well, what are the different subclaims there, and what are the evidence that you could provide? Or other kind of similar things like that. And I will tell you that some of you will have the instinct that will say, I will show you that my model has never in 100,000 instances done this, and I will say, great, that's not enough evidence, right? Like, think about other kinds of evidence that you can bake into your system. And you can end up making a structured argument that way. It works for many different kinds of safety in many different domains. But I'm not going to have you talk about that right now, because it is 319. And one of the strongest predictors of whether you get dinged at FCEs is how often you end on time or not. And so I hope everybody has a wonderful Wednesday afternoon. But I'm happy to take questions, of course, as usual.